All right, the last topic in this chapter is solubility equilibria. And for this, we're going to go back to an old kind of thought process that we were talking about all the way back in Chem 105 when we were looking at solubility equilibrium then. And it's the idea of solubility. Now, back in chapter 5, when we were talking about solubility from the standpoint of, okay, this is soluble and this is not soluble, and this is going to lead to a insoluble salt versus a soluble one. We were mostly talking about things in terms of kind of grounded, observable reality. Meaning, if I take calcium carbonate and I try to dissolve it in water, it's not going to dissolve in water, at least not very much. If I try to take iron 3 hydroxide and dissolve it in water, it's not going to do so very much. And on the flip side, if I put two solutions together and one of the products of that reaction is calcium carbonate, I'm going to expect to see a solid forming in the bottom of that test tube or in the bottom of that beaker. But with a better understanding of equilibrium, we can go beyond just simply soluble versus insoluble, and we can start talking about solubility more from a quantitative standpoint and understanding that solubility is actually a lot more nuanced than just soluble versus insoluble. And we can actually put numbers and thoughts to it, and we can actually start to talk about how we can manipulate equilibrium to get things that were previously insoluble to actually dissolve in water. And so let's go back to just a definition, base definition of solubility. By definition, solubility is defined as the maximum amount of a substance that we can dissolve in a particular amount of solvent at a given temperature. And so the given temperature that we usually use is 25 degrees Celsius. And the certain amount of solvent we use is almost always 100 milliliters. And so solubility is usually given to us in grams per 100 when it is presented to us as a numerical value. So the solubility of sodium chloride is 57 grams per 100. Whereas the solubility of calcium carbonate might be 0.01 grams per 100. Well, we can start to couch the whole idea of solubility inside of the process of equilibrium. And what we have to understand is that from a standpoint of solubility, every single substance has a point where it reaches equilibrium. And we can quantify what that equilibrium is using something called the solubility product constant. This is known as KSP. And KSP follows an equilibrium very similar to the ones that you've seen in other places. The only difference is that since we are talking about a solid product as one of the reactants, that solid does not show up in the equilibrium expression. So the expression for KSP is a product of the ions that will be generated by that salt when it dissolves. So for calcium carbonate, it would be calcium times carbonate because I get one of each. For something like manganese 2 hydroxide, it would be manganese times hydroxide squared because I would get 2 hydroxides out of that instead of just one. So with that in mind, let's open up Top Hat here and grab our next question. question, what is the solubility product constant expression for silver phosphate? And so the first question you'd have to ask yourself out of that is, well, what is the formula for silver phosphate? And if you remember that silver is a +1 ion and phosphate's a -3, the chemical formula for silver phosphate is Ag3PO4. So that would mean that it's going to break apart into 3 silvers and 1 phosphate. So what would that mean for its expression? And you're all exactly correct. Since I have silver here, so the concentration of silver ion would be 1, and it's going to be cubed because of the 3 in the equilibrium. And the phosphate ion would be there, and it would be to the first power because of the lack of coefficient there. So that is exactly right. And so this is what we ultimately see in any kind of solubility situation, is that the equilibrium that exists between the solid phase and the dissolved phase does have some sort of limit. And whether we're looking at something that is extremely soluble, like sodium chloride, or something that is relatively insoluble, like calcium carbonate, the fact of the matter is some of that solid is going to dissolve. And when it dissolves, it is going to get solvated, just like we saw in Chem 105, where the positive ions are going to attract the negative poles of the water, and the negative ions will attract the positive poles of the water, and they will separate the ions from each other that way by surrounding them with water molecules. But they'll do so in an equilibrium fashion. So as ions are being pulled off of the crystal, other ions will be getting reattached, and the rate of change will be basically the same in both directions once we hit that equilibrium point. Now, in Chem 105 terms, we call that point where we have hit the equilibrium, we call that saturation. A saturated solution is one where we cannot get any more solid to dissolve, and that is because we've hit the equilibrium point. And so when it comes to the question of, okay, how do I know when a precipitate's actually going to form in a reaction? The answer is relatively simple. Going back to our concept from last chapter about Q, I can compare the value of Q to the value of my equilibrium constant K, and that's going to tell me what's going to happen. Since solubility is the product here, if Q has not yet reached equilibrium, then we're going to continue to see dissolving take place. So if K is bigger than Q, we hit what is called an unsaturated solution. An unsaturated solution means that we have not hit the limit yet. And since we have not hit the limit yet, we're going to keep dissolving. If we do the calculations, however, and we find that Q is greater than K, then that means that we've hit the saturation limit and then some. And so not only will we no longer see dissolving take place, any of the extra ions that were present in those solutions prior to mixing are going to start to precipitate out into a solid. And that precipitate will form out until we get to saturation. So again, everything's driving toward equilibrium here. Now, the question in front of us is a relatively straightforward one. How do I go from discussions of equilibrium and KSP to calculations and discussions of solubility count, like what we saw with grams per 100? And the answer is actually relatively straightforward. There is a midpoint here that is very useful to us called molar solubility. Molar solubility would be moles per liter or moles per 100 milliliters, depending upon the unit that is given. And preferably, we would want it to be moles per liter, because if it is moles per liter, we know that molarity goes straight into equilibrium expressions. And so the question just becomes a matter of, how do I go from whatever solubility units I'm given into molarity, or vice versa? How do I go from molarity to some other kind of solubility unit? And generally speaking, we know that molar mass is going to be involved. Sometimes a conversion of volume is necessary as well. So if it's grams per 100, we would need to turn that into molarity by turning the grams per 100 into grams per liter first, which is a relatively easy conversion to do. So let's take a look at some example problems just to kind of get used to this. So, for example, the solubility of calcium sulfate. Calcium sulfate was one of those ones that we identified in Chem 105 as an insoluble salt. Well, turns out it is actually soluble to a little degree. 0.11 grams per 100 of water. Not really enough for us to notice, because rarely are we going to be measuring out that small of a quantity of calcium hydroxide. But the question is, well, what is the value of KSP? Well, the first thing that we would want to do is we want to turn this into molarity so that we can use it to find K. So if I have 0.11 grams of calcium sulfate in 100 milliliters of water, to turn that into molarity, I want to turn the milliliters into liters. So a simple conversion there would suffice. And then I want to turn the grams of calcium sulfate into moles. And for that, I'm going to need molar mass. Calcium is 40.08. Sulfur is 32.07. Oxygen is 16, and there are 4 of them. Total is 136.15. So calculating all of this out to 2 significant figures, because we only have 2 in the mass that we were given. 0.11 times 1,000, divide by 100, divide by 136.15. The molar solubility would be 8.1 times 10 to the negative third molar. And this is what we would call the molar solubility. Now, to calculate out an expression of K, we would set up an ice table. Calcium sulfate turning into calcium ion and sulfate ion. Now, here's the trick. Since calcium sulfate is a solid, we can ignore it completely. The ice table that we are going to create is based just off of the products. That's one of the reasons it's called the solubility product constant. And where do we start? Well, before we added the calcium sulfate, we had no calcium and we had no sulfate, which means that when we establish equilibrium, we will get some calcium and some sulfate, which means at equilibrium, our concentrations are going to be X and X. Now, here's the thing. Molar solubility is our X term here. And the reason we want to kind of focus on that is in this particular case, it's 1-to-1, so it's not going to be terribly difficult to make that conversion. One thing that we do have to be on the lookout for, though, is in those kinds of salts where it is not a 1-to-1 dissolution, molar solubility would change in those cases. So think about the silver phosphate that we looked at in the top hat question. That was 3 parts silver and 1 part phosphate. What would we do? Well, we would take that molar solubility and multiply it by 3 for the silver. Then we would cube it in the equilibrium expression. It's really easy to forget to do one of those steps in these kinds of calculations. But in this case, we can put the 8.1 times 10 to the negative third in for X, which is squared. So our KSP value is 8.1 times 10 to the negative third squared, which to 2 sig figs will be 6.6 times 10 to the negative fifth. So as far as solubility goes, what we'll always see, KSP values are never going to be greater than 1. If we have a KSP value greater than 1, we consider that to be a soluble salt. We don't deal with its equilibrium because we just assume it's going to dissolve. You don't see a whole lot of equilibria expressions for things like sodium chloride or potassium nitrate or any of those things that we consider to be highly soluble. KSP usually comes in for those things that we would have defined originally as insoluble to help us to get a handle on just how insoluble they actually are. And by all accounts, this KSP value is actually not that bad. calcium sulfate is a lot more soluble than some of the other ones that we'll see. All right. Any questions to start here? All right, let's take a look at another example then. First, we need to write the expression for a solubility product constant of calcium fluoride. And then, given the KSP value, figure out what the equilibrium concentrations for the calcium and the fluoride are. Okay, so this is kind of the other side of the equation here for problems of this kind. So the first part, the expression, well, calcium fluoride in the solid phase would be in equilibrium with calcium ions in the aqueous phase and 2 fluoride ions in the aqueous phase. The value of KSP would be equal to the concentration of the calcium ion multiplied by the concentration of the fluoride ion. And that fluoride ion would be squared because the stoichiometry is 2 for the fluoride. So again, nothing new here in terms of how to draw out the KSPs. Just again, slightly different use cases and variations in terms of context for how we would use these equilibria and the kinds of questions we could answer. Now, to answer this question about KSP, to find the equilibrium concentrations, we need to put out an ice table. So initially, we would have no calcium ion and no fluoride ion. We would see some calcium ion form and 2 times that amount of fluoride. So at equilibrium, we would add X and 2X for the fluoride. And again, this is where things can get a little bit batty for us. If we are trying to do this too quickly, it's easy to make really simple, dumb mistakes with KSP calculations. So 3.9 times 10 to the negative 11th is equal to X for calcium and 2X for fluoride. And the fluoride is squared. And this is all over 1 because there's nothing on the reactant side of the equilibrium. Again, here's where a common mistake can be made. I can't tell you the number of times I've seen someone with this exact kind of calculation tell me that it was 4x squared here at the end. And that's absolutely incorrect. You have to square both terms inside of the parentheses. So this is actually x times 4x squared, because we squared the 2 and we squared the x. So 4x cubed is the correct expression here. If I divide each side by 4, (9.8) times 10 to the negative 12th is equal to x cubed. I need to take the cube root here. I get x as 2.1 times 10 to the negative 4th molar. And again, 2 things to draw out of this. First of all, X is the molar solubility. So if the question were asking, what is the molar solubility of calcium fluoride? That is what you would write. You'd write 2.1 times 10 to the negative 4th molar. Now, the question wasn't asking about that. The question was asking, what are the concentrations? Concentration of calcium is X. So 2.1 times 10 to the negative 4th molar there. The concentration of fluoride would be twice that, 2x. So 4.2 times 10 to the negative 4th molar for it. but just something to keep in mind there. And to help with that, you'll see some references will actually start using S, capital S in KSP Equilibria ice tables to stand in for solubility. So if you run into an example problem online or even in the textbook where it shows this as S and 2S, that's why. KSPs are sometimes given S terms instead of X terms, just to help kind of remind you that that S is standing in for solubility, the molar solubility. All right, let's take it all the way back the other direction. What are the solubility and molar solubility of magnesium hydroxide at 25 degrees Celsius? KSP for that is 5.6 times 10 to the negative 12th. So this time we are being asked about the solubility and the molar solubility. So we start in the exact same place. Magnesium hydroxide, solid, in equilibrium with magnesium ion and 2 hydroxide ions. If I set up my ice table, I would have no magnesium, no hydroxide. I would gain some measure of magnesium, twice that much of hydroxide. So I have X and 2X. So KSP is equal to concentration of magnesium times the concentration of hydroxide squared. So X for magnesium, 2X quantity squared for hydroxide. So putting in the numbers now, 5.6 times 10 to the negative 12th would be equal to X times 4X squared or 4X cubed. Dividing side by 4, 5.6 times 10 to the negative 12th, divided by 4 is 1.4 times 10 to the negative 12th. For X cubed, cube root, I get 1.1 times 10 to the negative 4th for X. So I could solve the ice table if I wanted to. 1.1 times 10 to the negative 4th molar for magnesium, 2.2 times 10 to the negative 4th molar for hydroxide. I could also run that, since it is hydroxide, I could run that through a pH calculation if I wanted to, but we're not being asked to. So molar solubility would be just the value of X, 1.1 times 10 to the negative 4th molar. To turn this into grams per 100, what I would do is I would start with my 100 milliliters of solution, 1,000 milliliters in a liter. My molar solubility says that every liter of solution has 1.1 times 10 to the negative 4th moles of the magnesium hydroxide. And so the last step would be to turn the moles of magnesium hydroxide into grams. Magnesium, 24.31. Oxygen, 16, and there are 2 of them. Hydrogen 1.01, and there are two of them. 58.33 is the molar mass. Double check my math, make sure everything's canceling. Milliliters are gone, liters are gone, moles are gone. So I'm left with grams in 100 milliliters, which is what I wanted. So 100 times 1.1 times 10 to the negative fourth times 58.33 divided by 1,000. I'm getting 6.4 times 10 to the negative fourth grams per 100. So that would be the, kind of the true solubility there in red versus the molar solubility there in purple. Neither one of them telling a particularly great story about the solubility of magnesium hydroxide. And we kind of run into this problem across the board with hydroxides. Hydroxides in general are insoluble, which is one of kind of the confounding characteristics for why we have such difficulty with them as bases. A lot of them don't dissolve in water, or don't dissolve particularly well. This is also why magnesium hydroxide is kind of on the fence. If you do the calculations here, you look at it and go, I don't know, that pH is not terribly significant or impressive. You're talking about something that's just over 10. For a saturated solution of magnesium hydroxide. All right, any questions about these three examples? We've kind of seen how to work the calculations both directions, whether it's going from a KSP value to figuring out solubility, or going from solubility to figure out KSP, or some kind of combination in between. All right, then try this one here. The molar solubility for chromium-3 fluoride is 1.3 times 10 to the negative third. What is KSP for chromium-3 fluoride? Right, most of you gotten this far, so I'll kind of mark our progress here. Right, so most of you have come to, you have the equilibrium, you've made the ice table, you've even gone as far as kind of plugging up what the KSP expression should look like. Where we're getting bogged down is in detail. And So let's go back to what the question is giving us. The question is giving us the molar solubility of the chromium fluoride. Well, that value is S or X, depending on what one you want to use. So with that in mind, we already know that the chromium concentration is going to be 1.3 times 10 to the negative third molar. And we already know that the fluoride concentration is going to be 3 times that. So 3.9 times 10 to the negative third molar there. Where we were getting confused, some of you took that 10 to the negative third value and tried to turn it into KSP, tried to solve for X and figure out what X meant. Problem is, that's not what the question was. The question was giving you X and asking you to figure out what K is. So you've got to make sure that you're paying close attention to what the question is, what material you've already been given, and kind of what to do with it. And if you were in that camp that turned it into KSP, don't worry, you weren't the only one. A couple of you were down that road. So in this particular case, we didn't have to cube 3x and get 27x cubed or anything like that. We have the values. So 1.3 times 10 to the negative third for chromium and 3.9 times 10 to the negative third for fluorine. We just got to remember to cube that. We would get a KSP value of the product, which to two significant figures would be 6.4 times 10 to the, there we go. I'm sorry, 7.7 times 10 to the negative 11th. I must have hit a wrong number in my calculator initially. That makes a lot more sense. So that's the kind of thing that we're being asked to do there. And so again, it's really important when you get one of these solubility kinds of questions, take a pause. You know, obviously the ice table, that's easy enough to make. It's easy enough to get the equilibrium expression. Make sure that you understand what you've been given first, because that's going to tell you, do I need to solve for X or do I need to solve for K? Because that's really what you're ultimately choosing between usually. All right. Any questions here? Okay, so that's the kind of stuff that we would want to do if we were just looking at, I drop this salt into water, what happens? Well, let's start to explore some other kinds of things. Let's start to look at some factors that impact solubility. And the first thing that we're going to look at is we're going to call back to the very beginning of the chapter. We talked about the idea of the common ion effect. And we used the common ion effect to set up the whole concept of buffers. Well, we can't do that here in terms of there's no Henderson-Hasselbalch equation that we can fall back on for the common ion effect with solubility. But we can understand that the idea of the common ion effect is still true. If I have calcium fluoride and I'm dissolving it in water, Le Chatelier's principle says that it's going to dissolve a heck of a lot better in water than it is in calcium chloride or in sodium fluoride. And the reason is common ion. So if I add sodium fluoride and I up this concentration, Le Chatelier's principle says we're going to shift to get rid of the extra fluoride, which means that we're going to get less dissolved calcium and more of the calcium fluoride solid product. So that's one impact that we talked about. Now, how do we handle that from the common ion effect? How do we handle that from a KSP perspective? Well, kind of in the same way that we did before we knew what the Henderson-Hasselbalch equation was. If I know the quantity of common ion that has been added, I just add that as my initial condition for that ion. And then I see how the equilibrium expression changes as a result. So let's just take a look at an example problem of that. Determine the molar solubility of calcium fluoride at 25 Celsius in a solution that is 0.01 molar calcium nitrate. So setup for this is exactly the same as what we just were looking at. I've got calcium fluoride in the solid phase. In equilibrium with calcium ions and fluoride ions. And need to look up the KSP value here real quick. So if I'm in that same group of appendix tables here, if I go past the Ka and Kb values, I get these. And so I want to look up calcium fluoride. Calcium fluoride, 5.3 times 10 to the negative ninth. Now here's where things change up a little bit for us. Up until about a minute ago, we would have said that the initial concentration of calcium was 0 because we were just doing it in pure water. Now we know that the concentration, because it's a solution of calcium nitrate, that concentration is going to be 0.01 molar. Now we still have no fluoride present, so that part hasn't changed. And since we have no fluoride present, we know that we're still going to see the equilibrium moving toward the products. So I'm still going to gain some amount of calcium and 2 amounts of fluoride. But my equilibrium is going to look a little bit more complicated. 0.01 plus X for calcium, 2X for fluoride. Now, with the KSP value being 5.3 times 10 to the negative ninth, we're probably still okay to use the 5% approximation. I will warn you, though, because KSP propositions are not always one-to-one, and we're not always dealing with squared terms here, it's almost always a good idea to double check back if you are using 5% and make sure that your equilibrium concentrations regenerate this KSP value, or at least come close to it. And the reason I say that is because there are sometimes, especially when we're dealing with smaller solutions, where that ends up not being the case, and we have to go back and backtrack because, well, we assumed something that was not true. But again, we should be okay here, but we're gonna double check at the end just to be sure. So 5.3 times 10 to the negative ninth is equal to the calcium concentration 0.010 times 2x quantity squared. And so if we do out the math here, 5.3 times 10 to the negative 9th is equal to 0.010 times 4x squared, which would be 0.04x squared. Dividing each side by 0.04, I get 1.325 times 10 to the negative 7th for x squared. Take the square root to 2 sig figs. 3.6 times 10 to the negative 4th is x, which would be my molar solubility. So assuming that my 5% assumption is valid, which again, it looks like it should be, given the fact that our value here is to the negative 4th and our calcium concentration was to the negative 2nd. We'll double check to be sure. This is all that it asked us to do. It asked us to calculate the molar solubility. Let's just double check the numbers real quick and make sure. So 0.01 plus 3.6 times 10 to the negative 4th would give us 0.0103. So that's going to remain at 0.010. And then 2 times this would be 7.2 times 10 to the negative 4th. If I was going to just double check, 0.010 times 7.2 times 10 to the negative 4th squared. I would get 5.2 times 10 to the negative 9th. And that is close enough. Again, we're only off on the last significant figure. We're not off by a lot. That's a reasonable assumption to make. And again, just comparing the values, 0.01 versus 0.00036, it doesn't appear that the concentration of the calcium was going to change much. This is just one of those things because we are dealing with a more complex equilibrium than x times x, we can't just assume that the 5% is always going to hold up here. So the question is, what is the molar solubility? Molar solubility is 3.6 times 10 to the negative 4th molar. But again, we can see the impact here of the common ion effect, because we didn't do this calculation, but had we, the original molar solubility was 1.1 times 10 to the negative 3rd. So in pure water, about 3 times as much of the solid dissolves. Common ion effect pushes that equilibrium to the left and makes it less soluble. Okay, so this is one example of how a solubility equilibrium can be manipulated. In this case, for the side of lack of solubility. We can also look at things like pH. pH can have an impact. This is where it's good to have a good idea of how acidic or basic a salt is. So, for example, if I have insoluble bases, they will dissolve in more acidic solutions. So take, for example, calcium hydroxide. Calcium hydroxide is considered a strong base when it is a saturated solution or a solution in general. But we know that it has a solubility limit. However, if I lower the pH, what happens is that the hydrogen reacts with the hydroxide and Le Chatelier's principle takes over. We continue to see a movement towards solubility as that hydroxide gets reacted away. And the case for all these other ones is similar. Chromate ion is basic. So as it reacts with acid, it's going to start to form chromic acid, which is a weak acid. That's going to lower the concentration of the chromate ion. We're going to see more solubility as a result. Magnesium fluoride. Fluoride ion will form hydrofluoric acid, which is a weak acid. It's going to lower the concentration of fluoride. It's going to be more soluble as a result. Carbonate ions will form carbonic acid, which actually decomposes. They will make carbon dioxide and water. And so the carbon dioxide bubbles out, and the resulting solution becomes more and more soluble. These on the right-hand side, the silver chloride, the lead 2 iodide, these are not affected by pH, and the main reason they're not affected is their conjugates are strong acid conjugates. Hydrochloric acid, it's a strong acid. It stays split apart. Hydroiodic acid, hydrobromic acid, they all are strong acids. They stay apart. So adding acid and lowering the pH doesn't do anything, because the resulting product is just going to regenerate those ions and put them back into the solution. There's not going to be any net loss. And consequently, you can go the other direction as well. So if I'm looking at silver hydroxide, for example, silver hydroxide, AgOH, would be in equilibrium with silver ion and hydroxide ion. The KSP for this, we would have to look up, but we're already here. Just passed it. So for silver hydroxide, see what Google gives us. I'll take it from UMass. 2 times 10 to the negative 8. So setting up our ice table, we would have no silver initially, no hydroxide initially. These are the ones that we like because they're actually super easy. It's just x squared. So square root of 2 times 10 to the negative 8th is 1.4 times 10 to the negative 4th. So if I wanted to know the molar solubility of this solution, it would be 1.4 times 10 to the negative fourth molar. In this case, we're asked for the pH. And so taking the opposite of the logarithm of this, we would get that the pOH is 3.85. Which gives us a pH of 10.15. So on its own, silver hydroxide generates a pH of just around 10. Now the question is this: if the pH of the solution was set at 11, so let's say we're using a buffer, or in this case, we're using just straight up sodium hydroxide, what's the molar solubility going to be in that case? And so what we have to do is, okay, if the pOH is 11, or I'm sorry, the pH is 11, then the pOH must be 3, and the hydroxide concentration would be 10 to the negative third. Now we have the same equilibrium, but with slightly different conditions. This is a common ion effect, effectively. No silver, but now we have 0.0010 molar hydroxide. Our KSP is 10 to the negative eighth. So again, we should be okay to do the 5% approximation. So if we go 2 times 10 to the negative eighth is equal to X for silver and 0.001 for hydroxide. The concentration of hydroxide is going to be 2.0 times 10 to the negative fifth. And so that would be its molar solubility. And so what we would see is that because of the common ion effect, this basic salt would dissolve less in a basic solution. Now, by contrast, if I put it into an acidic solution, it would dissolve a whole heck of a lot better by virtue of Le Chatelier's principle. Acid would react with the hydroxide, pulling it out of solution. We'd see a shift toward dissolving as a result. All right, questions about either of these two? All right, so let's answer this question then. Which of the following salts are more soluble in acid than they are in water? So no calculations here. Can you identify where solubility in low pH would be more favorable. So the key to this particular question is identifying bases, in particular, identifying basic salts. Because the ones that are basic, the ones that have conjugates that are weak acids, those are the ones that are going to be more soluble in acid. So I need to be looking at the anions here and going, okay, HBr, that's not a good one. Hydrobromic acid strong. All it's going to do is just give me H plus and Br minus all over again. So that's really not going to help me out at all because I need it to remove something if I'm going to make it more soluble. So we can throw A out. For the carbonate, we get carbonic acid. Carbonic acid decomposes into CO2 and H2O. So as I'm increasing the amount of hydronium, I'm going to see that the calcium carbonate is going to become more and more and more soluble because the carbonate's going to keep reacting with that acid and going away. So that one's good. For the phosphate, I'm going to be looking at phosphoric acid. That really doesn't, that breaks down into H plus and dihydrogen phosphate, but not PO4. So that's good. That's gonna be more soluble. That's a weak acid to begin with. So let's be a little bit more accurate with that. It's gonna go both ways. Here I have an example of a hydroxide. Hydroxide's just gonna make water, so that's good. Silver chloride is going to make hydrochloric acid. That's going to break back down into hydrogen and chloride. So that's not going to work either. So it's the three in the middle. All three of those in the middle are conjugates of weak acids. And as a result, when we put them into a more acidic situation, they are going to react to form their conjugates. That's going to drive their concentration down. We're going to see a shift towards solubility as a result. All right, the last big kind of change that we can notice is through the formation of complexes. Now we've seen complexes in lab throughout the semester as we've been doing qualitative analysis, and really this is no different here. The only thing is that now we have kind of a way to frame why those complexes form and for what reasons. And so just a couple of terms here. The term that we use for the thing that attaches to the metal to make the complex, that word is called a ligand. Ligand. The term ligand describes what makes a complex, basically. Otherwise, we're just talking about ions in solution with each other. But as soon as those molecules or those ions attach themselves to that center atom, what we have is something called a complex ligand relationship, where the ligands have attached themselves to that center ion and have formed a complex as a result. Now, since this is an equilibrium that ultimately forms, we can express that equilibrium with an equilibrium expression. And the expression is known as the formation constant, which is why this is called Kf, formation for formation of a complex. And what we'll find is that it is calculated exactly the same way as the other equilibria that we've seen. The concentration of the complex is divided by the concentration of its constituents, the center atom and the ligand, um, squared up to however many ligands are attached. So in the case of this cyano complex, it's squared because there are two cyanides in that complex. Now, when it comes to doing calculations involving complex equilibria, we're not going to spend a ton of time on this because the level of application for it is relatively low. What I can tell you and what you would probably want to know is that it is there are two components to it. One of them is the equilibrium itself. One of them is stoichiometry. So, for example, if I wanted to know the amount of chloride that I needed to add to form this ferrochloro complex here, what I'd have to understand is that first I would need whatever the concentration of iron is, I would need 4 extra parts of chlorine. That's the stoichiometry. Then I would need whatever chloride was necessary to push the equilibrium to the value of Kf. And so it'd be two separate kinds of calculations that you would have to do there. But what you can see, and again, you've seen this to some degree in lab already, is that the formation of a complex kind of flies in the face of kind of what our conventional wisdom has been. This is insoluble, it's going to be insoluble, but if I produce a complex out of it, if, for example, I just inundate the iron 3 hydroxide here with enough chloride ion, what we'll start to see is that that chloride complex will take over, and what was once a big mess of solid will eventually just turn into a yellow complex solution. And so that's really, I'm not going to dwell on calculations for that because, again, I don't feel that the calculations for that are useful. They don't do a whole lot for us. But it is important to understand, and we've seen it in lab, that complex formation does impact solubility, and it does so in a positive sense. Things that were insoluble in water can be made soluble through the formation of complexes, and that there is an equilibrium kind of governing those complex relationships. And you've seen that. If you think about the Le Chatelier lab, you've got cobalt in water as a pink solution. You add chloride to it, it turns blue. You manipulate the equilibrium, it goes back to pink. It's not a set value. You need to have a certain amount of chloride in order to make the complex, in order to change the complex. And if you go away from that, if it becomes too low or you change the conditions, you make it more dilute, you heat it up, those kinds of things will impact the formation of the complex that you're looking for. So it is here that we're going to stop. This is the end of our chapter here. So go ahead and get that last point there. And so just want to give you the opportunity. I know we went a couple minutes over here today. I kind of warned you we might when we spent the extra time on the stuff from Friday. But Are there any questions related to um, solubility, equilibria, things that just jumped out as not making sense in the initial? All right, I feel like comparatively speaking, the equilibria that we just did are a lot easier than the ones that we were doing on Friday. A lot less complex, a lot less interpretation. You just have to kind of know what to do with the data. So, um, homework assignment tonight will focus on these equilibria from solubility. And then we'll have an opportunity tomorrow with the skill builder to kind of just practice everything to get ready for Wednesday's quiz.